We're going to broadcast.
The broadcast is now starting. All attendees are in listen-only mode.
Good morning. I'd like to welcome you to the first part of the InfiniBand Trade Association Fall Webinar Series, Why I/O is Worth a Fresh Look. Thank you for joining us today. Before we get started, I wanted to call your attention to the control panel at the top of your screen. Here you can see how you are accessing audio for the presentation and also ask questions. We encourage you to ask questions at any time by clicking Enter a Question for Staff and then entering your question. The presenter will respond to selected questions verbally at the conclusion of the presentation. Today's presentation is being recorded and will be available on the IBTA website on Monday. If you lose connection or experience technical difficulties, please know that the webinar will be available on the IBTA website. Now, without further delay, I would like to introduce our presenters, Paul Gruen and Jim Ryan. Paul Gruen is a chief scientist at System Fabric Works and has worked for more than 30 years on server I/O architecture and design, ranging from large-scale disk storage subsystems and RAID arrays to high-performance networks. He was also a member of the original InfiniBand architecture team. Jim Ryan is the chair of Open Fabrics Alliance, an organization that develops, tests, licenses, supports, and distributes Open Fabric Enterprise Distribution, and open source software to deliver high-efficiency computing, wire speed messaging, ultra-low microsecond latencies, and fast I/O. He is also a manager at Intel and has been with them for over 10 years. And now I think we're ready to begin.
Thanks very much, Rachel. Again, my name is Jim Ryan with Intel. I'll be sort of trying to ask questions of Paul to give him a chance to give us the benefit of his thinking and background on what's called Remote Direct Memory Access, RDMA, as well as InfiniBand, which is a specific implementation of a transport that delivers RDMA. I've had the privilege of working with Paul directly at Intel, and he and I have been involved with InfiniBand together for more than 10 years. The purpose of this series is to dig into I/O as a specific area of interest for IT managers. We think it's something that perhaps deserves a fresh look, perhaps a deeper look than it may have received in the past. So a lot of what we'll be talking about, we hope, is news and insights into I/O as it exists at the moment. This presentation is derived somewhat from what we call the InfiniBand Trade Association IBTA mini book, which is available on the IBTA website. I want to make it clear that neither Paul or I are trying to sell anything. We're trying to educate you on the importance and the benefits of RDMA and on the InfiniBand technology specifically. We hope we're talking to a broad audience of IT executives and managers and technologists. The format will be largely my asking Paul some questions and giving Paul, Paul a chance to talk about his views on RDMA technology. And as Rachel was just saying, we're asking you to submit questions during the course of this webinar, and I will collect these and put them to Paul at the end of this session. So with that, Paul, this webinar, as I've just explained, is meant to address I/O. But as I've also explained, we have a wide range of IT professionals that have been invited and, in fact, are participating in the call. How do you reconcile the focus on I/O versus the broad representation?
Well, good morning, Jim, and that's a really good question. I think it's safe to say that pretty much every I/O guy knows and understands the importance of I/O to the efficiency. Every IT guy knows and understands the importance of I/O to the efficiency of his data center. So, for example, if applications aren't communicating efficiently, we may be missing some pretty dramatic opportunities to achieve maximum performance in the data center. So even though it's sort of a cornerstone foundational technology that we may take for granted, we shouldn't lose sight of its importance. But even knowing that, even knowing how important I/O really is, who has the time to keep up with all the latest advances in something as basic and well understood and presumably settled as server I/O? So I think today, just as you were saying, Jim, we're hoping that we can encourage our audience to take a relook at what really is sort of a basic component of every data center. And it's a technology that we probably all think we understand pretty well. But there may have been some surprising developments over time. So it might be time to go back and take a look at I/O once more, maybe delve a little bit deeper, peel the onion back one more layer, and see what's really underneath as far as I/O goes and current developments in it. Before we do that, though, let me take just a minute and look at some of the pressures that might ring a bell with some of the IT professionals in the audience today. So, I bet that most of our audience today, you guys who are IT professionals and work in the industry day in and day out, you're pretty customer oriented, and your customers consist of your user community. And I'll go further and say that I'm going to bet that your customers tend to want better results, and they demand those results from you more quickly. They put some pressures on you to deliver a better product because that enables them to do a better job of whatever it is their task happens to be. Not only that, but often it probably turns out that they want to pay less out of their budgets for the service that you deliver. So you've got pressure to deliver more faster but at lower costs. And of course your natural instinct is to want to keep your customer happy, since that's probably how your performance is being measured. And of course your time is at a premium and you can't afford to disappoint your customer, so you probably tend to be pretty conservative in terms of applying new technologies and decisions about making changes to basic technologies that are driving your data center today. That doesn't really leave you a lot of time for thinking about really basic bread and butter issues like infrastructure and I/O. So this means that normally, if I've got this right, new technology gets injected into your data centers only when it solves some sort of a specific problem or has been shown to be absolutely bulletproof. On the other hand, you've also got this need to satisfy management demands, which can probably be neatly summed up as do more but do it cheaper. So somehow you have to do more for your customers, you have to do it faster and better, while at the same time you have to do it with less resources, less people, less budget, and less space. Yeah, and at less cost too.
I like your graphic, Paul. So one rock here is the increasing customer demands, and the other rock is the fact that management is not interested in giving you any more money than necessary. I suggest this is going to be a perennial need to look for opportunities to improve your operation as a data center manager.
Absolutely. And that can be a pretty uncomfortable spot to be in if you're that little sheep too. But there is some help for us over the horizon. This is where some evolving technologies may actually be able to help us out, some evolving I/O technologies. So here's a picture of sort of a standard, technology curve that I think we may have all seen before. The blue line being, performance going up, the red line being price going down. So it's a price performance curve. And it shows, transitions or advances in basic technologies like processors or server platforms shown in the bottom, or increases in things like network speed shown on the right. So we've learned as technologists that we can rely on this technology curve to help us out. We can pretty much rely on this sort of constant stream of improvements going on. Not only can we rely on it, but as technologists, we probably all come to expect these cool evolutionary improvements over time. See what I'm saying?
Yeah, I do. And I'm hearing you use the word evolutionary and basic technologies. Does that amount to sort of a satisfactory job description for the IT manager?
Well, satisfactory, no. Of course we have to track evolutionary growth. But there may be a lot more to it than just, paying attention to the next speeds and feeds in Ethernet or, the next core count in the processor. There might also be some more profound advancements that may have slipped past our collective radars that can really help us out going forward. So think about this. Nowadays, we're watching the emergence of some really interesting compute models like virtualization or its close cousin, cloud computing. I think those are all concepts that we've heard a little bit about recently, maybe even read about it, maybe even seen it advertised on TV lately. In each case, though, these interesting models, like the virtualization model, let's say, have driven the solution to some long-standing issue or obstacle, usually involving the need to reduce costs or improve performance. In other words, these things didn't just emerge, out of the blue of their own volition. they emerged in response to trying to address some kind of an issue or a problem. So let's think about virtualization for just a minute. So fundamentally, if you think about virtualization, it's really a mechanism that lets us just divvy up a resource, like a CPU resource or some other sort of a platform resource like adapter resources or so forth. It lets us divvy up those resources into finer-grained units. In this case, the units are contained in things called VMs, with which we're all pretty familiar. And that same concept of being able to take a coarse-grained resource like a server and divvy it up into smaller, finer-grained resources like VMs or virtualized device adapters is applicable to almost any data center resource like storage or virtualized networks. So you can see there that virtualization has really helped us move forward and solve a particular problem. But let me talk about that. Before the advent of virtualization, it was common for a data center to host one application per server. This may have made the management of server resources pretty easy, but as you can see in this next picture coming up here, it really led to this notion of server sprawl. So, if you've got this notion of one application for one server, which was, again, a common data center model, every time you decide to add a new instance of an application or you decide to add a new application, that translated to the addition of one or more new servers in your data center environment. This was okay for a really long time. It solved a problem and made management of server resources pretty straightforward, management of applications pretty straightforward. But it worked fine until we began to run out of computer room floor space or we ran out of power or until some other economic pressure drove us to look for more efficient solutions. The other thing about this is not only did this one server, one application model produce server sprawl that we've seen, it also delivered what I would call truly abysmal CPU utilization or server utilization rates. So various attempts have been made over time to address this server utilization problem through evolutions along the technology adoption curve. For example, there were attempts made to increase the processor thread count, coupled with attempts to create highly parallelized application to consume those threads. All of those were, at some level, attempts to increase the utilization of servers that we had in our data centers today. In this one server, one application model, you got a server sitting in the corner supporting a single application and loafing along at, something less than 5 or 10% server utilization. That's a pretty inefficient use of your resource. We also looked at things like more efficient processors that would let us attack the power consumption created by sprawl. A number of different technological approaches that were pursued, technology evolution approaches. But these didn't actually really address the underlying problem of compute resources being allocated to applications at a fairly coarse-grained level. So by really solving the server sprawl problem, we didn't really get there just by walking along the technology adoption curve. In the end, as it turned out, the solution to server utilization turned out to be server virtualization. And what that did is it allowed fine-grained allocation of server resources to applications as shown in this little diagram on the screen here. Nowadays, we're at the point where virtualization is pretty much a norm in most IT shops.
Well, I'm understanding now how innovation has come about to deal with some of the problems that have been around for some time, like server utilization and server sprawl. But I'm not making the connection between those recognized problems and the importance of I/O, other than the fact that I/O has been around as long as computers have been.
Well, think about it this way. Virtualization gave us a fresh way of looking at ways of allocating server resources. In the same way, a new look at I/O models can give us maybe a fresh way of looking at other long-standing issues that may be driving, our IT audience to distraction. Standard issues like improving efficiency, being able to provide a greater flexibility in how those fine-grained resources are allocated, or facilitating the adoption of new models like cloud computing. There's just a host of issues that are facing us, and I just keep wondering if at least a part of the solution to some of these isn't going to turn out to be, a fresh look at the basic I/O model. And in fact, we've already seen this happening in the HPC space. If you just look at the top 500 supercomputer list every year, you can see how low latency interconnects, or the emergence of low latency interconnects, have really largely transformed the way that large-scale clusters are built and deployed in the past 10 years.
It's probably me, Paul, but I'm just not getting it. I/O has been around, as I said a minute ago, since the creation of the computer. Obviously, it's sort of by definition, and it really hasn't changed that much. You have to have OS interrupts in order for the operating system to provide I/O services to the applications. The applications still use sockets or some other API to request the I/O services from the operating system. Data is copied through the kernel memory and into user space as it's delivered to the application. So, you know, given that background of things being the same and well established for many years, what's new?
Well, you know, you're right, Jim. The basic I/O model really hasn't changed a lot. It is, in fact, it's time-tested, it's proven, it's bulletproof, familiar, and it's also pretty inefficient. So that doesn't mean that there haven't been some relatively recent and pretty profound advances in the basic approach to I/O. So let's look at those just real quickly before we move on to what I would think of as the more fundamental changes that are occurring in I/O today. So if you look at this picture here, we're talking about, you know, the migration of PCI Express, or PCI, and we began with PCI as a parallel bus. It migrated from PCI to PCI-X and eventually emerged as PCI Express. So we managed to migrate an entire generation from parallel buses to serial buses. Now, this is a pretty disruptive change, but it didn't really represent a basic change in the I/O model. So even though it was a pretty profound change, we did get through it. Nowadays, server platforms are more performant than ever. So here's another example. Think about the speed bumps that have been going on in traditional networks. You know, the progression of Ethernet from 10/100 to 1 gig to 10 gig, and now today we're on the verge of 40 and 100 gigabit Ethernet. So these are pretty profound changes, but once again, they really just amounted to advances in you know, along the technology curve, not really a fundamental change in the way that we think about and use I/O. And there's other examples of this too that are maybe a little bit more significant, like, for example, the emergence of data center bridging. That allows us to do things like think about possibly convert to your unified fabrics. It allows us to provide better support for fiber channel, and there's a host of benefits that go with it. But again, it's really just an advancement of, you know, existing technologies that we've known today, in this case all the way down at the physical layer. But there are still some variations on the traditional I/O model. So think about it a little bit. You know, in retrospect, we may have been taking this basic I/O model for granted, and we may have even been forgetting to ask ourselves some questions, some basic assumption questions about how I/O works. And you put your finger on some of those a few minutes ago. For example, the use of, you know, a particular socket as a dominant I/O interface, the way that the application accesses I/O services through the socket's API, or kernel involvement as a component of the I/O subsystem. You know, I think that we all believe and understand that the way things work today, device adapters are owned by the operating system and allocated to applications for their use. But at the end of the day, it's the operating system that is really the major component of the I/O subsystem. And data copies. We assume that data copies are part and parcel of the whole process. So these are kind of basic assumptions that we've all been making, and we probably haven't stopped to think about them because that's pretty much the way I/O has always been done. As it turns out, there really are some pretty profound changes in the basic I/O model that are just now finding their way into the commercial enterprise data center. So starting with a clean sheet of paper, various initiatives have been formed over time with the goal of rethinking the basic I/O model. Eventually, those initiatives became what we know today as the InfiniBand architecture, which, as you pointed out at the beginning, is the best known implementation of what you would think of as remote direct memory access. And this all began with a really basic question, which really was, you know, what's the most efficient possible way for applications to communicate? And what are the relative figures of merit we would need to focus on if we wanted to meet the needs of those applications? So think about a set of figures of merit, so to speak, as a set of requirements that would drive the development of a new I/O architecture. Well, the most obvious one was latency, and that arose out of a desire to want to improve basically clustering performance, or improve IPC performance. So the first order of business was to be able to reduce latency. Beyond that, there were more significant issues, or not more, but other issues emerging over the horizon that I think gave us all pause in the I/O community. One of them was this relentless march forward in data rates, faster network data rates, which resulted in faster packet rates, which produced less processing time per packet, which meant that the CPU had to do a lot more work in order to keep up with these faster networks. So the second figure of merit turned out to be CPU utilization. And third, if we really wanted to relook at the I/O infrastructure and come up with a model that let applications communicate better, we knew we had to deal with bandwidth as well, storage as well. Storage tends to be bandwidth intensive, so we knew that whatever we came up with better have a pretty good bandwidth component to it. So that was a pretty aggressive set of goals that we started out with in the development of this RDMA technology. And it was pretty quickly obvious that achieving them meant we would need to revisit a whole bunch of comfortable old assumptions about I/O architecture that we'd made in the past. Specifically, what we needed to do was chuck those assumptions out the window. We needed to look at assumptions about buffer copying and find a way to get rid of those buffer copies, chuck that assumption out the window. We needed to get rid of assumptions about shared I/O devices and the way that applications share I/O devices. We needed to think about ways that applications actually access the I/O service, and a whole host of assumptions that really just had to go right out the window if we were going to come up with a new and improved I/O architecture. The result of all this was a really new way of thinking about I/O called remote direct memory access. So the whole point behind remote direct memory access is that applications are given direct access to what you really might think of as a message passing service. This is really advantageous to an application, since the lingua franca, if you will, of application communication really turns out to be messages. It's not streams of bytes, it's really messages. And we also felt that we needed to avoid the involvement of the OS. So those things together, applications given direct access to message passing, no need for OS involvement, and operations conducted as messages led us to what you might think of as a new basic I/O model. So let me illustrate exactly how that new I/O model works and what it's going to look like. Here's a picture of what you might think of as a traditional network architecture. So on the left-hand side, there's a server, and one on the right-hand side, and there's an operating system that supports some sort of a user application. Each application is going to use a well-known sockets API to engage the services of the operating system, represented in this case by that little dotted line right below the green user application. And what's going to happen is, as a packet arrives at the NIC, that packet is going to find its way up through the network stack. It's going to be delivered into an anonymous buffer, shown as that yellow buffer there, and eventually copied into user space, shown as the gray buffer in the user application space. That's going to consume a certain number of CPU cycles, and it's going to require a couple of context switches and at least a buffer copy or two. So here's some opportunities for really improving the basic way that we think about how I/O works today. What the RDMA network architecture does is it cuts through a lot of that cruft, and it does it by allowing the device adapter, if you will, the NIC or the channel adapter, to deliver data or messages directly into the user's application space. That's kind of the basics of RDMA and what it's really all about. So we eliminate this, the network stack, and we eliminate the related buffer copies, and we eliminate the context switch and the CPU utilization required to execute all of that. And by so doing, what we really have, instead of an I/O system as you've seen before, what we really have is an RDMA messaging service, shown as that green box that you can see. The application accesses this messaging service directly, so that means that no OS interaction is required once the messaging service has been established. And the cool thing about that is what we're effectively doing is we're extending user space all the way down to the point that the user actually touches the physical NIC. And there are protected mechanisms that make this a safe thing to do. So the best part about this is that the whole messaging service resides in user space. That's the way that we go about eliminating buffer copies. So That's really the method that we use that allows applications to communicate really directly with each other. What we've really created here is what I would think of as the notion of channel I/O. So we eliminate the OS and the I/O path, and that produces some dramatic improvements in efficiency. It allows data to be placed directly in application memory space, which results in the elimination of data copies through host memory. Since the CPU is no longer part of every I/O operation, demand on the CPU itself is to provide I/O services greatly reduced, which of course means that CPU capacity is now available for use in running user applications as it should be. And beyond that, there's been advances in the modern wire level transports and some big advances in fabric management that accompany this whole architecture. I haven't really talked about those here in this picture, but we'll talk about those in some detail in the third webinar when we talk about the details of the technology itself. So all in all, this has produced some pretty remarkable reductions in end-to-end latency. Really what we're doing is enabling servers to do much more real work in the same amount of time, but at a lower cost. So you can see how RDMA delivers really those three basic value propositions that we talked about before. It reduces latency, it reduces CPU utilization, and it reduces bandwidth. But what flows from those, and this is where I'm hoping that the RT guys in our audience will pipe up and really listen, pay attention here, is what flows from those is a host of what I would call higher level benefits. Some of those benefits, which are directly applicable in the data center are pretty obvious, like improved application performance, resulting from reductions in latency and improvements in bandwidth and so forth. But there's also a host of other, what you might think of as sort of boilerplate value propositions that emerge as well that we may not have thought too carefully about. Things like scalability in the data center, things like flexible allocation of server resources, the reduction in CPU utilization or improvements in CPU utilization, reducing the need for the number of servers in the data center. That reduces the floor print, which reduces power and cooling requirements, and so forth and so on. So there are a whole host of higher level value propositions that flow from the basic value proposition of the I/O architecture itself. Okay, just to close the loop on all this and to show how this new I/O model might actually open up some new approaches to computing, let me go back and talk a little bit about something I addressed just briefly earlier. Remember how virtualization came along and gave us a new way to look at server utilization? Well, in the same way, it seems that low latency I/O suggests a new way to look at efficient scalable computing by accelerating the emergence of clustering. So in other words, a change in the basic I/O model produced a new compute model, which produced a new way that we can look at scalable and efficient data centers. The rise of clusters really gave us a new way to think about data center design. So let me illustrate. For years, the database system that powers many enterprise data centers was considered the province of what you might think of as big iron or mainframe-based systems. So in the back of your data center, this big mainframe sat there and it hosted the giant database application. But then with the emergence of new clustering technologies that gave us entirely new ways of looking at database systems, there emerged a whole class of clustered database systems. Consider, for example, Oracle. So Oracle's products are all based on clustering and are all based on RDMA technologies that enable those clusters that let them deliver the highest possible performance in a clustered database system. Likewise with IBM's DB2 database system. For years, the world-renowned standard in database systems hosted on mainframe computers. With the advent of clustering technologies, all of a sudden it became possible to offer DB2 as a cluster implementation called DB2 PureScale. If you look at the IBM literature, they'll tell you over and over and over again that it's the emergence of a new RDMA model that enabled them to deliver PureScale as a clustered solution. So both of these solutions really emerged because the respective vendors were able to rethink the application of I/O, a fundamental technology that many believed had really long since been settled. So let me extend on this idea just a little bit, take it just a little bit further, maybe slightly into the realm of science fiction, but maybe not so much, and illustrate where this might potentially take us. So the picture you're looking at right now really is a traditional data center. I've shown it as a three-tier data center with a front end, a mid-tier, and a back end, where the back end, consists of a large database engine of some sort. Now, suppose that database engine in the back end happens to be a cluster-based data center, a cluster-based database system in the back end. What if, instead of running those mid-tier applications on the discrete servers that were shown in that top part of the picture, we were able to actually run them on a grid? So a grid that hosts not only the database cluster, but also instances of a mid-tier application. It's a little radical of a thought, but it's maybe an interesting thought if it gives us some new and interesting ways to allocate our existing compute resources between the mid-tier and the back end in sort of a fluid way. So it's just sort of an example of the sort of things that may happen if we rethink I/O more carefully. The point here is that we really may be missing some great opportunities to advance data center goals if we neglect a relook at I/O. In other words, if I/O is forgotten at our peril. And if you're going to do that, there are really two keys to successfully improving your data center. They're pretty obvious. The first one is a clear understanding of exactly the problem you're trying to solve. And the second one, which has really been the point I've been trying to make up to now, is avoiding the so-called unspoken assumption trap. The trap that occurs, the one where you don't even stop to question your own assumptions because that's the way things have always been done, so they never even occur to you as assumptions. We should peel those away and think really carefully about assumptions that we're making, such as the way that I/O has always traditionally worked. So really, here's where we've landed. RDMA has emerged as a result of a fresh look at I/O architecture, and in turn, it's worth taking a look at this new direct access I/O model because it lets us take a new look at how I/O can make actual improvements in the way we build and use our data centers. Sounds great, but I want to hasten to add it's not a panacea, even though it's a substantial change that does challenge our assumptions about how I/O works. But still, it deserves a careful relook, and it may hold the key to solving some important problems that our data center IT guys may be facing even today or in the near future. It is a disruptive technology, I should point out. I mean, we're talking no small potatoes here. But then again, it's true that we've all successfully integrated disruptive technologies before. For example, the emergence of PCI Express, virtualization has been widely adopted, and a host of other disruptive technologies have come along. So the point is that this doesn't really have to be a revolutionary change. There may be evolutionary paths available that will let us adopt new ways of looking at I/O for our long-term benefit. And that's what we're going to look at in our next webinar, coming up on October 21st. We'll explore some ways to begin the process of integrating this important technology into your environment without having to employ a fleet of forklifts in order to replace your entire infrastructure. There are ways to do this in sort of a smooth, coordinated, moving forward fashion that fits well with your normal upgrade cycle that lets you take advantage of improvements in I/O over time. And with that, if we have a little bit of time, I think we'd love to entertain a couple of questions. Jim, do we have any questions that are begging to be answered?
Yeah, we have a couple, Paul. Mostly along the lines of sort of practicality and application. You've given us some really interesting theoretical possibilities, and you've also sort of fessed up to the fact that this is a disruptive technology to adopt. So what occurs to I think our listeners is, how real is this? How do I consider implementing it? Who's offering us product? What's the nature of OEM adoption and support of this? You've given us a couple of major ISVs, for example, which is certainly helpful. But how would you characterize, first, the product availability for InfiniBand?
Well, products have been available since the early 2000s, and they've been on a pretty significant, technology improvement curve of their own over time. So the basic InfiniBand architecture has progressed from single data rate to dual data rate to quad data rate, and now we're on to 14 data rate, and not long after that is extended data rate. So, any technology worth its salt is always going to have a viable roadmap behind it. And that's always a good indication of a viable technology. If there's no roadmap, there's probably no growth. There are a number of pretty significant vendors in the marketplace providing InfiniBand products. I won't name any of them by name here, but I think we're all familiar with where these products are available from. And we're beginning to see, and this is the interesting part, we're beginning to see pretty broad adoption in some segments of the enterprise market space. For example, many members of the financial services community have begun to see the value of low latency interconnect in improving their competitiveness against others on Wall Street. So I think we are beginning to see pretty significant adoption in the enterprise space. Of course, InfiniBand or RDMA in general has been the dominant technology in the HPC space for the last decade or so. So it's a pretty well-developed technology being driven forward pretty aggressively by a computing segment with very, very high demands for performance. So I think we can rely on what we've got and what we'll have in the near future.
Well, let me ask you a follow-on question then. Is this a technology that's single-sourced? Is there kind of one architecture out there or one provider of this technology?
No, there isn't. There are multiple providers. I came from an environment, a product development environment, where you never used any component unless it was dual-sourced at least. And that's the case with InfiniBand in particular. There are multiple sources of InfiniBand products. Beyond that, there are approaches emerging, which we'll talk about in upcoming webinars, for delivering RDMA as a fundamental technology that don't require such specific use of particular InfiniBand-based products. For example, I'm referring now to RDMA over Converged Ethernet, which is a new method for delivering RDMA taking advantage of existing Ethernet infrastructure. So that should smooth the path to adoption and give people a lot of comfort in ways to develop and apply this technology.
Okay, so you told me that there are multiple sources of this technology. If I choose any one vendor of this technology, am I locked into their product line?
Well, that's something you'd have to discuss with the vendor himself, but let me point out one thing that didn't get discussed here in this webinar, but we will talk about in the third session when we get to the technology, which is the existence of a single open source software stack that equally well supports every implementation of InfiniBand out there. So once you've adopted that open source stack provided by the Open Fabrics Alliance, that means that you can support whatever particular implementation of InfiniBand you choose to use, whether it's Mellanox-based or QLogic-based or some other vendor's solution. They're all supported by this exact same open source software stack. That stack has been developed in the truest traditions of open source by a wide community of interested and enthusiastic developers who care for it, nurture it, and develop it over time, and have a real vested interest in making sure that it's a true open source implementation. So again, there should be a lot of comfort in our user community there in being able to adopt this technology without feeling like you're wedging yourself into a corner.
Well, then, just quickly as a follow-on question, let me shift to the OEMs. If I'm used to buying from HP or Dell or IBM, am I going to be able to work with them on an integrated solution that uses the familiar processors on the one hand and this new technology on the other?
Oh, absolutely. InfiniBand plugs into standard I/O buses just as you expect it to. So it's offered by the major OEMs as an option feature on virtually all of their products. I'm not completely up to speed with everybody's current product offerings from the OEM perspective, but I can tell you that it doesn't take a lot of looking to find OEM options available in virtually all of their products.
I'm getting a question in my window, and I need to read through it carefully because it's kind of a small window. With regard to multiple sources, how will interoperability in the data center be assured? The results from the IBTA plug fests are less than impressive. Will this improve with the next generation FDR product?
Well, the InfiniBand, there's a couple of answers to that. One is there's not just the IBTA plug fests, which are on a continuous path to improvement. There's also a series of interops that go on sponsored by the Open Fabrics Alliance, amongst others. So there is a great deal of effort within the industry to make sure that all these products do interoperate and that they do conform with the standard. So, I can't speak to the flaws that I think the questioner is asking about specifically, but I can tell you that it's a major concern of both the InfiniBand Trade Association, the Open Fabrics Alliance, and all of the vendors to ensure that all of their products interoperate. Quite a bit of investment is being made to be sure that that's true.
If I could just add quickly, Paul, the objective of the interop testing, of course, is to make sure that different suppliers of InfiniBand technology can work with others. And another key element of this is to make sure that the cable suppliers can keep up with the demands of increasing speed, such as FDR. So FDR in and of itself doesn't represent a functional change in InfiniBand, but it does represent another generation of demand of speed, and of course it incorporates the demands of PCI Gen 3.
That's absolutely true. And you would see that in the evolution of any technology speed. With each speed bump, you're going to go through a process of making sure that the products all interoperate.
Okay, with that, Paul, I think we're almost out of time.
Yep, we've actually reached the full 45 minutes. So thank you, Paul and Jim. And ladies and gentlemen, that concludes the first part of the IBTA Fall Webinar Series. Thank you for joining us. If there were any questions we were not able to get to during the Q&A, please email Paul. His email is up on the screen. And this webinar will be available on the IBTA website on Monday. The next webinar series is scheduled, or next part in this series is scheduled for October 21st, 8 a.m. Pacific, 11 a.m. Eastern. Thank you again, and you may now all disconnect.
Thanks, guys.